Hey guys, I want to do a quick 5 minute kind of overview of chi-square just to kind of finish up what we were doing in class yesterday. So again, here's our equation. It's chi-square. Again, we're not solving for x. We just leave that as it is the sum of observed values in an experiment minus the expected, which is based on the null, that everything's the same, squared over the expected. Okay, and the chart that I set up for you guys basically helps you solve this. So we had done this example in class where there was an actual experiment where our independent variable was different types of soil, and we want to see if that causes or there are different numbers of nematophores that come up. So here's the observed values. So this is the data that was actually taken. Okay, so this is what we went out and counted, our experimental results. The expected column, okay, so in these ones that you're doing tonight for, we call them ecology chi-squares, it'll be a little different than the genetics ones we'll do next class. But this number in the E column is going to be the exact same because the expected values are based on the null hypothesis of no difference. So it's basically a baseline. So if there was absolutely no difference, meaning if there was exactly the same number of nematophores in all four, that's our base, our null of no difference. And what we're trying to see is if this, the observed values, if there's a difference between this and this, that's what this chi-square is going to tell us, a yes or a no. Either this is close enough to this to be just considered pretty much the same and we're just off due to chance, like probability of randomness, or our observed values are not even close to the null of no difference, in which case we can say, well, there is a difference in number of nematophores in the soil. So the way I got 110, you take your observed numbers that are given to you or you get in an experiment, you total those up, and this is the sum. So if you add these numbers up, there's 440 total nematophores that were counted. I divided that by 4, okay? So, because we have 4 categories, and that's how I got the 110 in the expected column. Then this going across here, this is just math, okay? One of my classes we did it pretty well, the other we didn't. So you just take the observed minus the expected. So I just took 85 minus 110 and got minus 25. Again, the minus doesn't matter because we're going to square that number. So we're going to now take negative 25 and square it. And so the negative goes away anyway. So, I mean, you can write the negative if you get a negative in this column, but it doesn't matter because these numbers will always be a positive. So I took 25 times 25, negative 25 times negative 25, and I get 625. And then I took 625 divided by the expected, which is 110. And that gives me the 5.68. Okay, make sure you're dividing it by the expected, okay, not the observed. And that's supposed to be squared. My numbers are up. Then you take the sum of that. So once you do that for all 3 rows, you take the sum of all those numbers, because it's the sum of the observed minus the expected squared over the expected. So just add those up, and that is your chi-square value. Again, this is supposed to be like that. But so our chi-square is 11.44. Again, that's it. We're done. We don't solve for x. All right. So now we just need to look up that number on the chart to see if it's different or not. Okay. So to look it up on the chart, we need our chi-square number that we calculate here. But we also need the degrees of freedom. And remember, the degrees of freedom is the number of categories you have minus 1. And since we had 4 categories here, the degrees of freedom is 3. So we need 3 and 11.44. And we're going to look that up on the chart. Okay, so here's our chi-square chart. The critical value, remember across the top, it gives us the probability, which is basically, this is a percent or a probability that the results we got would be off from the expected. Like, how likely is that due to chance? So how often would that happen? And so like this 0.90, that means that the probability is 90% of the time we would get the results that we did off of the null by chance, which means if it's by chance, we can't conclude that it's because of our independent variable. Okay, so we're either off here, this is either different enough from this to be say, whoa, it's not likely chance, it's not probable that it happens randomly. So then we conclude that our independent variable really made a difference here. Or if this is not off due to, if we have a high p-value above 0.05, then that means that the little bit that we're off from the null of no difference is just likely to happen randomly anyway due to chance. And so we can't make a conclusion that our independent variable caused any difference. Okay, so somebody has decided that a probability of 5% or 0.05 is where we kind of make the line. Okay, so this number is your critical value. So when I ask you on a chi-square problem, I'm going to ask you, first to solve it. I want to know what your chi-square number is. I want to know what your degrees of freedom are. Okay, and then on the chart you look up, so we're at 3 degrees of freedom. Okay, and so we're going to read in this row, and we're going to read over and try to find our chi-square value of 11.44. Now, you're not going to find exactly your number here. See how the numbers, the chi-squares, are going up as the probability that it happens randomly goes down. Okay, so the bottom line is you find our 11.44, which, if we go all the way over, it's probably right here somewhere. Okay, it's a little greater than 11.3, but so it's, if I ask you now for the p-value, again, it's not exactly 0.01, but you can just say the probability or the p-value is a little less than 0.01. That's what you can say. Or if you want to estimate a number, okay, something in this range here. But the important thing is where it is. It's less than the probability is less than 0.05, meaning, let's say it was at 1%, just to make it easier. What that means is the probability is 1% of the time you would be off how much you were off from the null just due to chance. So that's not very likely. So this is like, the 99, getting 99 heads in one tail. That was way off of our 50-50 in our coin flip example. And so what that means is, to us, this is where we kind of want to be. If we want to make a conclusion about our independent variable making a difference in the dependent variable, we want our chi-square numbers to be on this side. Okay. Also, keep in mind, this is important, a lot of times your chi-square number may not even be on the chart. It may go way off the chart, like way over here. I think on the first one you get like a chi-square, it's like a 70-something number maybe. Okay, and people are thinking they're doing it wrong. You're not, but keep in mind what that means. If your chi-square is 70-something, you keep going. That means the probability that it happens randomly is getting smaller and smaller. So that means there's a huge significant difference between what you observed and what you expected based on the null. All right, so that's what I'm gonna ask you. So if in this question, if I asked you what's the critical value, you give the 7.82, since we're in the 3 degrees of freedom column. Then if I ask you what's your conclusion, you say, because we're on this side of it, we say there is a significant difference between what we got or observed and what we expected based on the null. So there's a huge difference, okay? Which means we reject the null. And what this means is our independent variable, we see a difference in our dependent variable from the independent variable. We can maybe make a conclusion. If it's on this side, if it's a probability of 10% or greater that it could happen randomly, we're not allowed to say that we cannot conclude that our independent variable caused a different result in our dependent variable, okay? So we say that whatever we were off from the null is likely due to chance, and that's it.